Okay, I would like to introduce the next part, the AFLOW prototype. So please log into the website s4e.ai and open this website. Click the workshops here and click the AFLOW prototype to open my Hopkins notebook. Okay, let's continue. So my name is Xiao, and from ROSEI group, I will take this part. And yeah. First, I require you to click the runtime here and click the disconnect to refresh it. Okay, so let's reinstall the AFLOW. Wait a minute. I'm sorry. I'm sorry. Let's continue. Okay. So please click the list button to install the AFLOW. About 30 seconds. Okay, so I'm gonna run a test to see if we install it properly. Okay. Now we can start. So why we need the AFLOW prototype? We can expand this part, and it means we need AFLOW to do our materials modeling. So we first should let the AFLOW know what the material is, what the material look like. We cannot just simply tell the AFLOW that I want to titanium oxide and please give me an output. It's not possible. You need to make the AFLOW knows what's the structure. So there is an example. So the word site. So this is a kind of minor. If we want to know the thermal properties or electric properties using the VAST calculated, we need to let the AFLOW to know about this material. How to know that? If we have a microscope that can enable us to look at down to nanometer scale, and we can see that the material consists of repeat unit cell with a periodic arrangement. So inside the unit cell there is atoms. So just this atom forms a certain structure with a certain location and also the diameter of the space, and just repeat it periodically and to form our material. All we need is to let AFLOW know about this structure inside. So including the volume of the unit cell, the length, and the diameter of the atom, maybe it's already inside AFLOW, and the distance between two different atoms and the atom's location. This kind of figure is maybe not obvious, so we use the ball and stick model to provide a clear view of the atoms and bonds throughout the model. So you can see that it can clearly shows where the atoms sit inside the unit cell, and they are identical. Okay. So how do we let the AFLOW know that we cannot put the figure inside the AFLOW directly because the AFLOW cannot read the figure? So we need to design the label for the crystal and ensure that each label corresponding a certain crystal structure. In this case, we use this label. It consists of 4 parts. The first one is shows the stoichiometry of this crystal and Pearson symbol, space group number, and Wyckoff letters. If we have time, I will introduce all of them. And what you currently all need to know is that we just use these 4 parts, and we can let AFLOW know the structure, and this label corresponding to unique structure, only one. And also at the same time, we need also to let the AFLOW know that this label tells where the atoms sit, but it not tell the distance between the atoms and also the length of the boundary. So we need to define the AFLOW parameters, describe degrees of freedom. For example, in this case, we have four degrees of freedom. A describes the length of the square at the bottom. Because this kind of structure, this one is square, so the A represents this length and also this length. We also need the C over A, which controls the height of the crystal. Between this, if we lower this number, it will compress the crystal to let AFLOW know we find between the height of this crystal. And also the Z1 and Z2 is control the distance between each atom. So by put the label in the AFLOW and provide the parameters, we can exactly let AFLOW know what we want to calculate. Here is an example. So how do we let the AFLOW know? We just use this command line, which consists of AFLOW and the double short dash proto equals to our label, and the double short dash parameters equals to our degrees of freedom. You can simply run this command. Yeah, it will give us the output and contains the structure, and that can label by the mask. And it has our command and the space group number, where the reference come from, and also the lattice vector ABC, and where the atoms sit and their position. So we all know that this kind of output is fit for the vector calculation. It's the same as this format. So if we what can we do to change the format? Sometimes we need SIF, and we need some different files for different software. So AFLOW can do this by simply add tag. For example, if we want to do SIF output the SIF file, we simply add the double dash SIF followed by the command and run it. Yes. So we can see that the output is pretty different in the format, but the content is the same. So they describe the same structure, but it converts to a SIF file. And you can use this SIF file to fit in the XRD software and to do the refinement. Yes. Also, if we want to do other format, we just simply, for example, if we want to put it to this modeling software and to be let it readable, change this SIF to AS. Sorry. Run it. Yes, this is a format that can be removed by ACE and show QE SCQ. quantum espresso. It changes the format as well. Have it init. You can see the difference, right? So it enables us to output different format of this structure. Okay, so we know that how to generate prototype and to let AFLOW know about the structure, but you notice that it's only a structure. It's it do not provide a compound name. For example, if we want to titanium oxide, it will not know it's titanium oxide. It's just a structure. We need to decorate the atoms in the structure. So how we do that? Here comes to the next part. How we create more geometries with the elements. First, I will give you the first example, the rock salt structure with a label here and with magnesium oxide. We need to generate this kind of structure. Yes. So the structure is represented by this label. So we just need to put the atoms inside. You can simply do this by input the AFLOW -proto equals to the label and use a comma to let the AFLOW know that we want the magnesium and the oxide. And we define the params by run this. You can see that we already let the AFLOW know that where the atoms sit. If you can remember the previous one without this, it output here is A and there is B. And now it can let AFLOW know that the A side is magnesium and the B side is oxide. So what if we want to change the position of the magnesium? For example, in this command, it lets, for example, just the magnesium here and oxide here. How can we let the oxide sit here and magnesium at the other side? We cannot do to just simply make the magnesium, the oxygen here and the magnesium here. No, we cannot do that because we need to strictly follow the alphabetic order here. So here must be the magnesium and it must be oxide. Must follow this order. So otherwise it will not really don't know what we need. So for the AFLOW. So we can add the dots AB here to specify the A side is a magnesium and the B side is oxide. So if we run this command, you can see that it's exactly the same for this one. Because if we do not specify, it will set by default that A side is here and B side is here. What we should do is only change the order of this AB to BA to make this reverse. Like this. And now you can see that the magnesium is located at 0, 0, 0 for the AB, and here the magnesium is located at 0.5, 0.5, 0.5. They just change the place as a place. However, for this example, where the magnesium and the oxide state is not very important because they are identical. So for the following, the second example should be the more obvious. This gives us a structure with a prototype. This is a label and with aluminum fluorine. What's the difference is that it's AB3. Means aluminum sit as A, and in each unit cell there is one aluminum inside, but 3 fluorine atoms. So we want to generate this prototype. We can by replace the label here, just copy paste it, and AB set the A is aluminum and fluorine is B. Put the parameters inside, run it, and let's see. Yeah, It will give us aluminum with seat at this position and one aluminum and 3 fluorine. If we want to change the position, we just need to change the AB to BA. Right. So here are 3 aluminum and 2 fluorine. And if we do not put AB or BA here, it will default that the aluminum is seated at A and the fluorine is seated at B. Notice that it will you cannot put the fluorine here and the aluminum here because it strictly follow the alphabetic order. You just need to remember this. And here comes the third example, or the last example. We have the structure inside, and it has three atoms, 3 different atoms, A, B, C, and with silver, nitrogen, and oxide. And it's pretty simple. Just copy paste the label here, replace the label, and determine where is the A, which atom is the A, which atom is B, and which atom is C. And try to run this, and the output give us exactly what we want. And if we want to change the order, for example, we want to silver is seated at the B side, nitrogen is seated at the A side. We just change this label here to BAC. Which means silver is B, nitrogen is A, and the oxide is C. You can see that the position has been changed. The silver located at here and the nitrogen place. So if we do not put the ABC here, it will default by distribute the atoms by distribute the silver to A, the nitrogen to B, and oxide to C. See that the output is identical with this one, with this ABC. Okay, and so if we want to do, we come back to the magnesium oxide case. So here we put the 3.5, which means we let them know the degrees of freedom of this boundary. This of the boundary. So if we put -1 here, it will enable the automatic volume scaling based on the atoms. And when this, it can fine-tune the lattice parameter and also the volume of the structure. So I just introduced how to generate the AFLOW and to generate prototype to let the AFLOW know what structure we want and where the atoms sit. So there are different functions for this code. We can modify them to make the process more easier. So for example, if I give you these complicated, maybe a little bit complicated a prototype and with this label, and but the degree of freedom is pretty so many freedoms. So you don't want to just type it by yourself. It's a tedious process. So what the AFLOW do is that it's just labeled for you. For this one, this set of params is corresponding to the 001 label, and you just need to modify your label and add the slash the dash 001 and to let the AFLOW know that the degrees of freedom the parameter set is this. So you can run both, and you can see that it's readable and the output is exactly the same. So what if we don't know about I'm not very sure how many parameter sets under this kind of a label. So we can just run without the label, without anything. Run it, it will give us the error. And in the error, you can see that the 1 is corresponding to this parameter set, 2 is this parameter set, and 3 is this one. We can find what we want and use this code to generate it. So yes, we are now ready to create the AFLOW files, and with our prototypes, we just let the AFLOW knows about the structure we want, where the atoms sit, and what kind of composition, and what next is we want to integrate it into the AFLOW files to be ready to run the WASP calculation. So the example here use other kind of prototype is another prototype that's readable by the AFLOW. It's not very common. I recommend you to use this one, this label, because this do not provide us the chance to change the degrees of freedom. But it is a good it can be used to just teach you how to generate the AFLOW. So we just need to modify the code to add AFLOW here and design the prototype and distribute the elements. And yes, so this line of the code can generate AFLOW file. And this line is that we read this file and see the output. Okay, it created the AFLOW file. Contains all the modules inside we want to calculate, maybe, and also the WASP settings. And here comes the structure, exactly the output, and it will be integrated into the WASP setting. And if we run the AFLOW in, it will start the calculation. So what if we want to generate AFLOW in at multiple times? Because, for example, if we want to calculate if we want to decorate one prototype with different atoms, for example, we also want to copper at A side and also silver at the A side, gold at A side, iron at the A side, and if we run many comments, it's tedious. So we just use a comma to separate each kind of elements here, and it will automatically go to generate the silver, manganese, zinc, and the next is the gold, manganese, zinc, and copper, manganese, zinc, and iron, manganese, zinc, and silver, titanium, zinc, and generate multiple AFLOW with a single command. And what if we want to have a multiple prototype? We can also use a comma to separate the prototype, and it will go through this prototype first and decorate the atom by the sequence, and also next go to this prototype and decorate the atom. So we can click the one and see they are already they can generate at the same time. So how we know about the AFLOW prototype label? So where can we find about all of the prototypes and search what we want? So one option is we run this AFLOW -- protos and to see the library. You can see that output shows the library, and we have all of the prototype inside. You can search what you want, and you can also just visit the website. This is the AFLOW website, and click the prototype index here. This is also the library. You can just search what you want, and if you want to get more information, just click it, and you can see the structure, all the information you want. Okay, if you want to search from the database, you can use this command by running the AFLOW and prototype labels. Search for the prototype labels. Define the number of species you want, the stoichiometry, and also the space code. So it will return the result automatically. And if you want to get more information about the command to achieve different functions, you can run this with me. See all the commands available, so you can combine them together to achieve your goal. Okay, I introduced all the information about how to run the flow prototype and construct the structure, distribute the atoms, and that's the machine node. So I give you 3 exercises. You can do that. It's pretty simple. I give you maybe 15 minutes to finish it, and I will show the answer. And see if you can run it by yourself.
Can we ask a question?
Sure.
So for the magnesium oxide, the parameter is equal to 3.5. I know that's a degree of freedom, but like why is that? Like why do you think the parameter is equal to 3.5 versus for other compounds you have a series of
It's because of go back to the magnesium oxide. This one? 3.5, this one? So this is because for this structure, the CFA means it's pure and simple. It tells us it's a cubic structure. So what is cubic? It means the length is the same as A, B, C, X, Y, Z. The length is all the same. So the degrees of freedom is just the lattice parameter is only the 3.5 is A. You can change this 3.5 to what you want to change the structure.
The parameters, they're defined based that I can vary the parameter space and it stays the same label. So depending on the prototype label, you might have additional parameters that you can vary and you don't change the space group, for example. So it actually gives you the degrees of freedom that maintain the structure. So these prototypes are they're not a single structure, they're actually an infinite series of structures with different parameters. So it just depends on which structure you have and how many degrees of freedom it has to keep it in the same space group. Does that make sense?
So does it only happen when the structure is symmetric?
When the structure is what?
Symmetrical.
Well, all these structures have some sort of symmetry, right? So the space group is a collection of symmetry operations, right? So do I have a mirror of my face? This is one operation. Do I have a translation that keeps the structure the same and allows me to all these operations constitute the space group. And so the degrees of freedom say I can shift the structure, I can change the structure and warp it in this way, and I don't change the symmetry operations.
That makes sense.
Yeah. Anyone have any questions on that? It's a little complicated, but it's a very useful construction. It allows us to generate many different types of structures very quickly. You can think of it kind of like a SMILES. I don't know how many of you are familiar, but Oli's brought it up earlier. This is kind of the SMILES construction, but for structures. So you can think of it as like a hash for the 3D structure consolidated into one string. It has all the information you need to make a structure. That's the utility of this construction. Any questions?
Just start with the exercise.
change its yes, it's not. It increases. Yes, it's actually good. So so the lake will change, but the symmetry actually increase. So you're looking at you have the same space where you gain some, you actually form a super. There's relationships between certain space groups where you have operations between higher symmetries. So you can either stay in the same space, that's also allowed. Sometimes by shifting the parameters, but it's not like 167, because the travel is not linear like that. So I don't know what 166 is. This is hexagonal. I have to look. There's a hexagonal structure. Oh, I think it goes from hexagonal to all hexagonal structures are not. Is that what happens? I think it goes around. Check.
Corey, how do you decide on which free?
No, it's not a decision. It's by definition of the structure. So you can think of
Sorry, it's been a while since I took structures.
no. But listen, they also don't cover these things in structures too much. Remember that these definitions are actually they're in the construction of the Wyckoff positions. Did you guys cover that?
Yes.
You might have said the word, but maybe you didn't go into much detail. So the Wyckoff positions, if you go look in the ITC, the International Table for Crystallography, all of these space groups have, they're defined with respect to the Wyckoff positions and how there's equations. They actually tell you how you can change the Wyckoff positions and keep the same space group. So it's not a point, it's actually lines and usually there's atoms. There doesn't have to be atoms, but usually these sites have atoms. So you can move the atom along the line and the space group doesn't change. I need to qualify that because the example he's going to give you, it actually changes the space group because it goes to a higher symmetry. So you either you keep the space group or you go to a higher symmetry.
Okay.
Yeah. Do you mind if I take the screen real quick, just to show a nice picture? I think it's going to help a little bit. It's okay, I got it. So for those of you that haven't studied space groups before, I just want to show you this nice picture. So this is coming from a paper that we published on how to calculate the symmetry. Okay, so a little bit of history. The symmetry of 3D structures that are periodic. It turns out that there's only 230 unique space groups. Okay, so in three dimensions, there are 230 different space groups. Okay, and so despite the fact that we've known since the early 1900s that we have 230 space groups, the ability to calculate them precisely, this is something that's very difficult to do. So the implementation of this is hard. So for those of you that are interested in learning a little bit more about the symmetry, I refer you to this paper, but what I want to show is this picture. Every crystal structure has some sort of symmetry operations with them. okay? So there, depending on which way you look at the structure, you can define these mirror planes. So somewhere in the structure, if you can define a mirror plane, like the face, I have a mirror plane that goes straight to the face. I have one side that is the same as the other. So I have a mirror plane through my face, okay? You do the same thing for crystals. You define mirror planes are one type of operation, and the other type are these rotations here. Let me make it a little bigger. So you see that I can do rotations, and it keeps the crystal the same. So I can rotate, let's say I can rotate by, a mirror plane is actually a two-fold rotation, because I can fold my face twice, and I can get back to the same position. So getting the set of these operations within the crystal define the space group, okay? And so what we're looking for for these structures is what is the space group as defined by these operations, and then more importantly for the label, what are the degrees of the freedom in the structure that allow me to keep those symmetry operations. So maybe I can move my atoms all together in such a way that I maintain the mirror plane. That's the idea. And so the degrees of freedom tell me that. And depending on the structure, some have more degrees of freedom than others. The first degree of freedom is the same for all the structures, and it's the scaling factor. Because you can always uniformly increase or decrease the volume and maintain all the symmetry. So the scaling factor is always the first parameter. Okay? So that's the idea. It's a little tricky. It took many years for us to understand. Actually, this code has been in development. It was in development for 15 years until it was really solved. And so, and by the way, the software in AFLOW is the best. Let me show you. It's very complicated because you have to deal with tolerance issues, experimental issues, imperfections. So if you look at this, we did a big comparison among a lot of different packages that can calculate the space group of a structure, right? So if you get an experimental structure, someone says, hey, this is the structure, tell me the space group. Our software does it better than everyone else. This is telling us is how many mismatches are there out of a set of all the different types of structures that exist. So you see that there are some softwares where they experience tremendous number of errors, particularly for the hexagonal space groups, okay? So it has trouble with these 3- and 6-fold rotations. They're very tricky with it from a tolerance perspective. AFLOW does this in a self-consistent way. So it calculates all of the symmetry parameters and tries to find a consistent spatial tolerance. Because basically we want to understand, at some level, what we're doing is basically we need to check if I perform an operation and I rotate my crystal, at some point I need to see, are the atoms right on top of each other? And what is the tolerance, spatial tolerance, to say that they are overlapping or no, they didn't overlap. So figuring that out in a way that I don't need to provide the parameter with human intervention, that the code can figure out the tolerance by itself, that's what AFLOW does. So we run this code for 4 or 5 million structures without defining the tolerance value. It figures it out for us, based on which gives a symmetry profile that's most consistent. All the details are in this paper if you're interested. It's very tricky. The devil's in the details. All right, I give it back to you.
Okay, I think time is up, so I just start provide the answer. So the for the first exercise, we use the command AFLOW-PROTO and copy paste the label here. Here I use the and example and enter the parameters here. -1 for first and 0.5 is this one. Silver A values, and we use a pipe and to run these two commands simultaneously. We add this kind of command to provide the physical class. For the 0.5 is it's 166. Create another line. Copy the command. Just write 1.1.0. And that's all. And all the and this is answer for the first exercise. And you just go through all the parameters and then write it. Or just run it and get the result. And for the second we generate two structures with parameter -1. Silver is located at D. Oh no. First structure. Silver at D. Copper at D. Ion is at ADIES. And we can get the add parameter -1. Yes, here the result. And do the second, in the order here. And for the third one, generate structure, we use just use the delimiter, the OSG for provide us a space group and call for optimization. write down this space group number. Let's try this. Okay, write down the Pearson symbol and icon. Yes, you know the backup position. So you combine them together and to follow this step. Yeah, follow this prototype command and generate. And know how to convert this hard-coded prototype and to the prototype label. Okay, so I think I still have some time, so I introduce some of the crystallography. So we know that we cannot directly tell the flow that the compound name only. For example, we tell the flow that we want to calculate the sodium chloride is no, we need to provide more information. And if we just only tell the AFLOW the structure, no atom position, no compound name, and no symmetry, AFLOW can also don't know what to start. So we need to define the symmetry, the position, and structure, and the compound name at the same time. And the AFLOW also have the prototypes inside, which name 001. That kind of name is it's a hard-coded prototypes and no degrees of freedom for us. But we generally use this type of protocol that can give us a flexibility to change the structure. So why we need this? Can we just not provide the space group or not provide Pearson symbol to just let the AFLOW know structure? The answer is no. We need to provide all of them because the Pearson symbol is a symbol that can tell us the structure, and it generally consists 3 letters, three components. The first one is a lowercase letter, which specifies the crystal family. For example, for the CF8, it's C means the cubic, and the uppercase letter it means the centering type. For the F, it means all base centered, and the number, the last number means total numbers of atoms seen in the combination cell. But if we only have the Pearson symbol here, we can show that for this structure, these 3 structures, they all share the same Pearson symbol, but they have totally different structure inside. It's because we need this space group number to specify symmetry inside. For example, for this zinc sulfide, and it's with this structure, and but for the rock salt, they share the same Pearson symbol, but it's totally different structure. So we need both, and so that's why this label is designed like this format. Okay. So if we want to go more information, I recommend to go to the AFLOW school and watch the video provided for them. Okay, that's all for the AFLOW prototype part. So I would like to take any questions you have. There are any questions?
How does the order of the CDPA change? Like change the results when you change the order?
Sorry. Can you repeat that question? 4.2. Okay. Yes, 4.2.
So we are changing the capital CDPA, their orders. But what happens if we change the small CDPAs?
You want to change this CDBA?
Yeah.
I think you can just change it, but it's not very common. It's a part of the.
But what is the function of it?
It shows the Vical position. The Vical position is where the atom sit.
But not why not ABC?
I think it has special means. Don't change that.
Yeah, because the results change when I change.
You try to change that. I think which means it's already defined. Do not change that. Yes.
What is the space group number?
Sorry.
What's the space group number? Like 216.
You want to know what's this group number?
Yeah, what's the meaning of
it means symmetry. We have the higher the number is, it means there are a lot of different type of symmetry. Higher order of symmetry. For example, if you can visit this. Where's the website? You can here go to the prototype, the space group. They're all space group number here. And the higher the number is, the more symmetry side. Check each of them. Yes. Show the symmetry of this the crystal. If you no other questions, I will let the how to introduce the child part.